Have you ever wondered how electricity gets from a giant power plant all the way to your home to light up your room or charge your phone? It travels through wires in a special way called an alternating current, or AC. Unlike the steady, one-way flow of electricity from a battery, which is direct current or DC, AC electricity is constantly changing direction. It kind of wiggles back and forth like a wave. This wiggling nature is super useful for sending power over long distances, but it also introduces a fascinating concept. In this world of alternating current, the voltage, which is like the electrical pressure, and the current, the flow of electricity, are like two dancers. Sometimes they move perfectly in step, but other times one leads and the other follows. This relationship between the voltage and current is incredibly important. Think about it. For your devices to work properly, they need the right amount of power. Power is what does the actual work, like spinning a fan motor or heating the coils in a toaster. In an AC circuit, the total power that the power company sends out isn't always the same as the useful power that your appliances can actually use. Some of it can get lost or returned to the source without doing any work. Understanding the dance between voltage and current helps engineers and scientists make our electrical systems much more efficient. It helps us make sure that the power being sent is actually being put to good use. So why does this matter to you? Well, inefficient power usage means wasted energy. Wasted energy costs money and puts more strain on our power plants and the environment. Imagine you're pushing a friend on a swing. If you push at the exact right moment as the swing moves away from you, your friend goes higher. But if your timing is off, your push isn't as effective. It's the same with electricity. When the timing is off in an AC circuit, the system becomes less efficient. This concept of timing and efficiency is what we call power factor, and it's a key idea in the world of electricity. In the next few sections, we're going to dive into what power factor really means. We'll explore what happens when the current dancer leads the voltage dancer, and what happens when it lags behind. We'll also look at the ideal situation, when they move in perfect harmony. By the end, you'll have a clear picture of this fundamental concept that keeps our modern world powered up. It's a core principle not just for electrical engineers designing the grid, but for anyone curious about the invisible forces that make our technology tick. Let's get ready to explore the amazing physics of AC power. So what exactly is power factor? In the simplest terms, power factor is a number that tells us how effectively an electrical device is using the power it receives. It's like a grade for electrical efficiency, on a scale from 0 to 1. A power factor of 1 is a perfect score, meaning all the electricity being supplied is being used to do real work. A lower power factor, like 0.7, means that only 70% of the supplied power is actually doing something useful. The rest of the power is just sloshing back and forth in the wires without accomplishing anything, like pushing a wall. You're using energy, but the wall isn't moving. To understand this, let's break down the power in an AC circuit into two types. First, there's real power, also called active power. This is the good stuff. It's the power that does actual work, like making a light bulb glow, a motor spin, or a speaker produce sound. It's measured in watts, which you've probably seen on light bulb packages. Then there's reactive power. This power is a bit different. It doesn't do any real work, but it's necessary for creating the magnetic and electric fields that some devices, like motors and transformers, need to operate. It's like the energy you use to build up momentum on a swing before you can really get going. The combination of real power and reactive power gives us something called apparent power. This is the total power that the power company has to supply to the circuit. Think of a glass of soda. The soda itself is the real power. It's what you actually drink. The fizzy foam on top is the reactive power. It takes up space in the glass, but doesn't quench your thirst. The entire contents of the glass, soda and foam combined, represent the apparent power. The power factor, then, is the ratio of the soda, or real power, to the total drink, or apparent power. A glass with less foam has a better power factor. From a physics perspective, power factor is all about the phase difference between the voltage and current sine waves. When voltage and current are perfectly aligned, meaning their peaks and valleys happen at the same time, the power factor is 1. This is the most efficient state. However, certain electrical components can cause the current wave to shift, so it's no longer in sync with the voltage wave. This time difference, or phase angle, is what causes some power to become reactive instead of real. The bigger the time gap between the two waves, the lower the power factor, and the more foam we have in our electrical system. Now let's talk about what happens when our two dancers, Current and voltage fall out of step. One common situation is called a lagging power factor. This is what happens in circuits that have a lot of what we call inductive loads. Inductors are basically coils of wire, and they are found everywhere, especially in things with motors. Think about your refrigerator, your air conditioner, a fan, or power tools. All of these devices use magnetic fields to create motion, and creating those magnetic fields takes a little bit of time. This causes the current to get delayed, so it lags behind the voltage. Imagine you are pulling a heavy cart with a very stretchy rope. When you start pulling or applying the voltage, the cart or the current doesn't start moving immediately. It takes a moment for the rope to stretch and then for the cart to start rolling. This delay is exactly what happens in an inductive circuit. The voltage is applied, but the current takes a moment to build up and catch up. This time, lag means the power factor is less than 1. This is the most common type of power factor issue in industrial settings, and even in homes with lots of motorized appliances, leading to inefficiency in the power grid. On the flip side, we have what's called a leading power factor. This situation is less common in everyday life, but is very important in electronics and power systems. A leading power factor is caused by capacitive loads. A capacitor is an electrical component that stores energy in an electric field, like a tiny, super-fast charging battery. In a circuit with a capacitor, the capacitor wants to charge up right away. This causes the current to rush out ahead of the voltage. In our dancer analogy, the current dancer decides to start its move a split second before the voltage dancer does. You can think of a capacitor like a small empty balloon connected to a water pump. The moment you turn on the pump, or the voltage, water, or the current immediately starts flowing to fill the balloon. The flow starts before the balloon is even full or has much pressure built up. This is why we say the current leads the voltage. This effect is used intentionally in many electronic circuits, like in the flash of a camera or in power supplies. Engineers also use large banks of capacitors to deliberately create a leading power factor to cancel out the lagging power factor caused by motors, which helps balance the whole system. Finally, we arrive at the ideal scenario, the unity power factor. This is the perfect score, a power factor of exactly 1. It happens when the current and voltage in an AC circuit are perfectly in sync or in phase. Their sine waves rise and fall together in perfect harmony. In this state, there is no reactive power at all. All of the apparent power being supplied by the utility company is converted into useful real power that does work. The foam in our soda glass has completely disappeared, leaving only the refreshing drink. This is the most efficient way to transfer electrical energy. Unity power factor occurs in circuits that are purely resistive. A resistive load is a device that uses electricity to generate heat or light directly, without needing magnetic or electric fields to operate. The simplest examples are classic incandescent light bulbs, the old-fashioned kind with a glowing wire, electric heaters, toasters, and electric stoves. In these devices, the flow of current is directly proportional to the voltage applied, with no time delay. As soon as you apply the voltage, the current flows, and the filament starts glowing or the coil starts heating up. It's a direct, instantaneous relationship. So why is achieving a power factor close to unity so important? For power companies, a low power factor, either lagging or leading, is a big problem. It means they have to generate more total apparent power to deliver the same amount of useful real power to their customers. This requires thicker wires, larger transformers, and more fuel for the power plants, all of which costs a lot of money and increases energy loss in the transmission lines. Because of this, large industrial customers are often charged extra by utility companies if their factory has a poor power factor. They are given a financial incentive to be more efficient. This is why power factor correction is a huge field in electrical engineering. Engineers install capacitor banks to counteract the lagging power factor from all the motors in a factory, or they use advanced electronics to make devices behave more like simple resistors. Even in our homes, modern power supplies for computers and TVs are designed with power factor correction circuits to ensure they draw power efficiently. By striving for unity power factor, we make our entire electrical grid more stable, reliable, and economical. It reduces waste, saves money, and is ultimately better for our planet, all by making sure our electrical dancers are moving perfectly in step.